Now, one aspect of models that physicists are very good at is to put uncertainties on your model predictions. Now, this is something that most pundits, most experts don't do. You listen to the TV news and someone says, we think interest rates will go up 2%, or we think the bank will do this. They don't say plus or minus 3 or somewhere between February and March. They don't give uncertainties. They sound confident, but evidence suggests that these experts are actually doing no better than monkeys throwing darts. It's entirely random whether they do well or not. Uncertainties, however, physicists are trained to think that a number without an uncertainty is meaningless, and this is an unusual mindset in the real world and an incredibly useful one. Now, in the general world, uncertainty is seen as a bad thing. If someone's uncertain, they're seen as indecisive, waffling, not good. But in fact, knowing the uncertainty on a number can be incredibly useful. Imagine, for example, that there's a particular investment and it's predicted to return 10 plus or minus 2%. Now, in this case, the uncertainty doesn't make a fundamental difference. So it might be 8%, it might be 12%, no big deal. But what if it was predicted to return 10 plus or minus 20%? The average return is the same, but some years you might lose 10%, and some years you might gain 30%. But that makes things quite different. If you, for example, were a company offering this, you might have to worry about negative returns. What happens if you have a year when it goes negative? Are all your customers going to pull out? You've lost me money. Maybe they'll have to take a margin call. Maybe they need to hedge the risk. It makes things quite different. If on the other hand you've got 30% improvement in one year, everyone's going to flood in, you might need to hire more people, and then they're all going to be disappointed when the next year you get 0% or something like that. So knowing how much these things are going to jump around makes a fundamental difference to how you run your company. Another example of where uncertainties matter is in low probability, high consequence events. For example, let's imagine that global warming has a 5% chance of shutting down the Atlantic meridional, overturning circulation and plunging Europe into an ice age. That's important. It may only be a 5% chance, but it'd be a catastrophe. If you load a new weapons system to Ukraine and it causes Russia to start a nuclear war with 2% chance, is that going to affect your chance of lending this weapon to Ukraine? Small but very consequential things can have an enormous impact, and so knowing about them is really important. But then why is there an uncertainty in your model predictions? Why can't you predict what's going to happen? Well, one possibility is you're just missing input data. For example, weather forecasts. If you knew the temperature, pressure, humidity and wind speed at every point in the atmosphere from the surface to many kilometers up and all the way over the oceans and the deserts, then maybe this wouldn't be an issue. But of course, you've only got weather stations in a few places and a few weather balloons and a bit of satellite data. You don't actually know what the temperature, pressure and density is in most places in the atmosphere. So you have to interpolate somehow between the places where you do have the data, which is going to be not quite right. Likewise, if you're modelling the spread of COVID, you don't know exactly who's got it until it's too late. Exactly how many people have got it, you haven't tested everybody, you have to make guesses and assumptions or assume it's at random or something like that. So again, you're starting with uncertain parameters. You don't never know everything you need to know to initialize it. And of course, even if your initial data was perfect, you had to make approximations to build your model, and these approximations may be imperfect. Again, for disease models, you may not know precisely how infectious a disease is or what fraction of people who catch it die until you've got better data. So principally just wait until you've got better data, but you often can't do that. If you're a policymaker and you have to make a decision, you often can't wait for things to become clear. In a pandemic like COVID, for example, every day you wait, the number of cases could be doubling. So the longer you wait, the much harder and more people die, and the much harder it is to do anything about it. You've got to jump in early to fix a problem, and that means you could be making a mistake because early on you really don't know what's going on. The data is crap. So you're stuck in a really hard situation. You have to act early, otherwise it could be too late. But early, you don't know how bad it's going to be. It could be that maybe this pandemic will not be a serious problem and you're going to massively overreact. And you don't know, but you have to make the decision. Then you can't wait. Climate change is another classic example. If we wait until climate change is immediately obvious and all the uncertainties have gone away, it's too late. The climate has already changed. So we have to make decisions now, and right now we don't know in that much detail what's going to happen. So we have to make our best guess and just hold our noses and go for it. And that's a typical issue for policymakers with uncertainties.